Hello and welcome back. Today we're going to be creating our AI nav pathfinding, and this is going to be the code that will be generating the path for the AI to actually crawl on the ceilings and stuff. That being said, this is going to be a very large subject, so we're going to be splitting it into two parts. The first part is going to be going over how to create a path that will move along the ground, jump up onto the wall or the ceiling, and then move along the wall or ceiling and have the chance of jumping back down and have all of that be very fluid and just work with the AI as it currently stands. It's also going to be having code to handle the grounded state, as we need a enum to determine whether it's on the ground, in the air, or on a wall or ceiling. Then we're also going to be working on some error handling to make sure that if the AI happens to get closer to the next waypoint due to physics or what have you, as this is a physics-based AI movement, then it will go ahead and just jump to the next waypoint instead of trying to get to the current waypoint. And then we're also going to be doing a check to see if we have been trying to get to a waypoint for too long, we need to go ahead and generate a new path to try and get to the target location to make sure that the AI doesn't get stuck too much. We're going to go ahead and dive into a Blackboard real quick before we get to the code, and we'll use that to kind of break down what the current objectives are and how we're going to be achieving them. All right, we're in the Blackboard here. This is kind of where I originally started. My intention was to create a 3D model that would represent all of the navigatable areas, much like an auto-generated nav mesh that would be on the floor, but this would actually wrap around the surface all the way up to the ceiling and all the pillars and everything. This would allow navigation anywhere on any of the surfaces in the game. And the way this works is you take a point A and a point B, that's the origin point and the target point, and the nav mesh will find the two closest points on the mesh and then navigate through the mesh in order to find the closest distance. And it does this through some wizardry on the back end that I'm not too concerned about. Then it creates a series of waypoints which are marked in green here. Now this does work, but the problem wasn't actually with the nav mesh. I ended up running into the problem when it came to authoring the nav mesh. So this is kind of what I actually got to, and what it amounts to is a sculpted out 3D model that is then shrink wrapped to the scene geometry to create a nav mesh. And this was very slow to create, and I realized about halfway through, when I got about this much done, that this was going to be pretty much impossible for me to recommend anyone to actually make besides myself. And since I couldn't recommend it to anyone else to make, I figured implementing it into the project really wouldn't be viable. So what I decided to do was something a little bit different. So first off, we have our level geometry, and that's in white here. Then we have the auto-generated nav mesh, and that's in blue here. And say you want to get from point A to point B. The automated nav mesh, just like up there, will go ahead and create you a path, which is a series of waypoints from point A to point B. Now these waypoints are highlighted in green. So my basic idea was, using this path, I can typically decide that there will be geometry somewhere in the ballpark of this path. So every so often, say about 10% of the time, we'll go ahead and decide that we want to be on the ceiling or on the wall or what have you. So from one of these points, say we decided this right here. We'll go ahead and create a raycast, which will pick a random direction upwards. Let's say it goes over to the right. And using that, it will go ahead and find the location on the wall that counts for this. This will create a jump target. Now, what this will do is when the AI is coming along, instead of continuing on to this node, it will now jump towards this node and attach to the wall. And then because of this raycast being successful and us knowing that there is a wall up and to the right of this, we'll go ahead and reuse this same ray further on for every node as we progress. Now, there may come a time when that node will be incorrect or simply too far away from the wall, at which point we will decide we now need to go ahead and move back down to the ground. And at this point, the AI will go ahead and jump down. This creates a new path that allows the AI to run, jump up onto the wall, run along the wall, and then jump back down. Now, in practice, this actually looks pretty good. The movements are fairly organic, and this allows the AI to pretty much interact with any environment. The only downsides being that it really doesn't work well with extremely tall rooms. So if you have a room like the entrance up here, the AI aren't really going to run all the way up the entrance, because generally they're trying to get from their location to your location. And that doesn't really necessitate going up the entrance further. Now, there are a couple issues with this. Say, for example, you have a second path that instead of going in between the pillar and the wall, goes outside the pillar. And say you're already running up the wall, which means that these rays are cast every so often, and the AI's current position is actually on the wall, running along. Now, this ray right here would actually impact the pillar, and thus the AI would believe that it should run along the wall and then run all the way over here, and then run all the way back to the next point. And obviously this is incorrect. This is impossible. So there's a couple safeguards that I ended up taking to resolve this. First off, anytime it is raycasting along like this, if the raycast point is more than about 25% greater or less than the original raycast point, then it will go ahead and just break out and go back to the walking position. This will allow the AI to kind of handle any pillar. It just kind of snaps out of running on the wall when there's a pillar between it and its original path. Now, this does result in them coming off the walls fairly frequently if there's a lot of pillars in the environment, but it also doesn't look half bad, so it gets the job done. Now, besides that, we also have a slight issue with overshot. So due to the way we're actually jumping up onto the wall, it's very conceivable that we may end up actually farther down the path than we had originally intended. So I do a little bit of math to resolve this. If the AI's actual position is closer to the next waypoint than it was to the previous waypoint, we just go ahead and erase the previous waypoint and go on to the next waypoint. And that's pretty much it. The end result is now we can have AI run along the ceiling, run along the walls, and jump back down and interact with each other in a fairly fluid and natural way. Now, that being said, the path generation and the actual navigation of the path we're going to be breaking up into 2 separate videos, as they are fairly complex subjects, and I don't really think I could get a single video with all of it without it being excessively long. So we'll have this video this week, and then next week we'll actually go over how to make the AI move along it. That being said, let's go ahead and dive in and get started. All right, so hopefully you have a bit of an understanding of what we're going to be doing today. So we're going to go ahead and dive straight into code. Now, there's a bunch of functions that we need to do before we can rewrite this physics process, as the physics process is going to kind of iterate through the path, and then once we've reached a target destination, we'll go ahead and be killing that path. But in order to do that, we need functions to handle the creation of paths, the destruction of paths, and the stepping through of paths. So first off, we're going to be starting off with exports, then we're going to be doing all the functions, then we're going to be coming back to the physics process and going ahead and wrapping it up there. Let's go ahead and get started. First off, we're going to be creating a new class. And if you're from C#, this is going to basically be like a struct in C#, and we're just going to be passing in the waypoint position, normal, and then a Boolean saying whether we're on the floor or not, and an estimated waypoint duration. This is just going to be used to do error control to make sure that if we get stuck, we go ahead and repath if we've been trying to get to a waypoint for too long. Now, I didn't realize this when I first started this project, but you can actually create little subclasses like this and then use them in the script like structs in C#, and we're going to be using this pretty extensively going forward, so we're going to be starting with this. This will be our little path waypoint object. Now below that, we're going to need a signal, and the signal is just going to be launch request. This will be used anytime we need to launch from the floor towards the ceiling or vice versa. And it's going to be kind of different than a normal jump, as the jumps are just used to move around the environment, whereas launch is used to actually transition from one path state to another. And that signal will just be listened to on the limb controller in order to jolt the AI from the floor to the ceiling or what have you. Now next up, we're going to go ahead and create 2 export groups. The first one is going to be path navigation. That is actually going to be used for the velocity and things like that. We're not going to use that navigation agent though. And the second one is going to be for path generation. Now the path generation is going to have a lot of export variables, but the path navigation is going to have just the maximum velocity as well as the velocity change and another float for the minimum launch delay. We're just going to use this to make sure we don't spam the launch request and we don't end up bouncing around the environment really fast. I'm gonna go ahead and delete that physics process as we won't be needing it just yet. And down here in the second export group for the path generation, we're going to create a fair few variables. The first one is going to be the debug active variable. That's just going to be used to draw a line wherever the AI is going, and it's going to be defaulted defaults, but later on this will be invaluable to determine if the paths that we're generating are actually ideal. Then we're also going to have a ground check distance, which is just going to be used for the grounding code, as well as the stopping distance, which is the distance that we use to stop before we get to a waypoint. This is going to be exactly like Navigation Agent 3D. Next up, we're going to have something called a wall roof distance change allowance. This is just going to be a percentage from 0 to 1, representing 0 to 100%. And it's going to be the distance from the origin of the path on the wall to whatever the distance from our waypoint currently is. This is a little bit hard to explain, but I explained it in the whiteboard. Basically, all this means is that if we vary too much from our distance that we're stepping up to get onto the wall, then we'll go ahead and just snap out of climbing on the wall and go back to the floor-based pathfinding. Next up, we're going to have an up path check distance. This is just going to be the distance from the waypoint that we're willing to check for an environmental path. If you do this too crazy, then you might end up never actually being able to reach certain parts of the ceiling or what have you with the jump velocity, and you may need to work on the jump velocity. And then we're going to have a world collision matrix, and this is just going to be using the export flags 3D physics, and we're going to be passing it an int, which is world collision. You can see over here we already have that, and if you select over here, you can just select world, and that works out just fine. And last but not least, we're going to have a chance of up path. This is between 0 and 1, representing 0 and 100% chance. And the chance I tend to set around 10% or 0.1, and you can set this to whatever you like. If you set this too high though, the AI will never come off the ceiling, and it just looks kind of funny. You end up with an empty ground below you and a whole bunch of AI all over the ceiling. There's a couple private variables. The first one going to be the desired velocity. Then we're going to have a target position. That's just going to be wherever we're currently pathing to, as well as a last retrieved path waypoint, which is of type path waypoint. And this one's going to be used anytime we want to get our current desired location. Following this, we're going to go ahead and create a grounded state enum. Instead of just using a boolean to say whether we're on the ground or not, we actually have to use an enum, because since we can be on the wall, we need to determine whether we're on the wall, on the floor, or in the air. Speaking of which, we're going to go ahead and have a current grounded state, which we're just going to default to grounded state.none. And we're also going to have a current ground normal. Now, we do have a normal that's just the last retrieved path waypoint normal. So that's whatever the desired normal of the path waypoint is. So if we're on the ground, it's just going to be vector3.up. But then we also have a current ground normal. And every time we check for the grounded state, we're going to be getting the normal based off of that. And so if we happen to be running on the wall, we're going to have this be the actual proper truth of what the normal of the wall is, as opposed to what the desired waypoint's normal is. And this is just necessary for some basic code for making the torso rotate properly to the wall that it's climbing on. Next up, we're going to have initial wall roof distance. This is going to be of type float, and it's just going to be defaulted to 0. This is going to be used with the wall roof distance change allowance in order to determine if we should snap off of the wall or not. Next up, we're going to need a couple timers. The first one's going to be the launch attempt interval, and that's just going to be used with the minimum launch delay to make sure we don't spam launches. Then we're also going to have the waypoint failure timer, which is just going to be used with that estimated waypoint duration up there to make sure we aren't stuck. Just below that, we're also going to have the internal gravity scale. This is going to be whatever our current gravity scale at the launch of the game is. We're just going to set it to the gravity scale. We're going to use this to reset the gravity anytime we're on the ground or in the air. And then we're going to be setting it to 0 when we're actually on the ceiling, so that way we don't immediately fall off the ceiling. Then there's a couple variables here that are a little bit different. We're going to have a RNG, or a random number generator, and we're going to be using this throughout the entire process for any sort of determination that needs to be random. So we just cache it here so we don't create a bunch of extra memory. We're also going to have a current path, which is going to be an array of path waypoints. We're going to be removing the first one in line each time we get to it using the stopping distance float up here. But the current path will ideally always have something in it, as it will be navigating around. And then anytime it's just standing still, the current path count will be 0. Then we also have a RID of the nav map. Now this one's a little bit weird. This uses the RID, which is kind of a pointer to a location in memory or an object in memory. And the nav map is going to be pulled from the 3D world that the AI is in upon start. Now the nav map is actually this blue mesh here, and it's used for the navigation. It's kind of auto-generated in editor using Godot's tools. And we're going to be accessing that via nav map so that we can kind of create our own paths without use of a navigation agent 3D. Now that we have all of that out of the way, we can go ahead and create our ready function. And there's a couple of things we need to get done first. We're going to be getting the nav map from using the function getWorld3D.navigationMap. And that's just going to return any navigation map in the world. Then we're also going to be setting our internal gravity scale to the current gravity scale, which is just that value right there. And last but not least, we're just going to go ahead and randomize our RNG and create a new random F range between 0 and minimum launch delay, and assign our launch attempt interval to that value. This is just going to make sure that whenever the AI all spawn, we don't have them all immediately jumping at the exact same interval, or otherwise it just looks kind of funny. Now next up, we're going to get into all the functions. We're going to be starting with the set target function. This is going to be passing in a vector3, which is going to be our new target. And first off, we're going to go ahead and clear our current path and randomize our RNG. Then we're going to be creating a new path, which is just going to be an array of vector3 pulled from the navigation server 3D.mapGetPath function. And we're going to be passing in that nav map that we went ahead and assigned, as well as our global position and our target position, as this function requires an origin and a destination. Then we're also going to be passing it in false as the optimized path boolean. And this is just going to make sure that the path is not optimized. It has regular waypoints at a very high density. The reason for this is we want the density to be nice and organic and as it moves through the environment. If you set this to true, you will actually get much better optimization. Now we're going to create a couple variables that are going to be used throughout this path generation function. And these are going to be the current up vector, the last waypoint, the last on ceiling, which is a boolean, and the current path chance, which is a float. So the current up vector is just going to be whatever the normal is. So that's going to start out by vector3.up, and then we're just going to assign it based off of the environment as we move through it. And then the last waypoint is going to be whatever the last waypoint is, which starts out as the global position, but as we iterate through this path, it will be set to whatever the previous one was, as well as last on ceiling, which we're going to default to false, but here in a second we're going to assign that. And then we also have the current path chance, which is going to be the chance of up path divided by the new path.size, as I want the chance of up path to be based off of the entire path, so it'll be 10% of all paths, not 10% of all waypoints, which are two very different values. Now, next up, we can go ahead and check to see if our last retrieved path waypoint, that means we have been moving through a path already. We're just going to set our last on ceiling to whatever the current waypoint not on floor value is. And this means that if we are currently on the ceiling and we're repathing, we're going to start out on the ceiling. That way we don't create a lot of noise in jumping up and down all the time. And before we get started on the new path for loop, we're going to go ahead and create a new space state, which is just going to be using the function getWorld3D.directSpaceState. This is going to be how we interact with the environment using raycasts and things like that. Now we can go ahead and create a for loop. Now we're going to iterate through all of the new path, and we're going to call each one the waypoint, and then we're going to be assigning these to the current path array as new path waypoints. So let's go ahead and get started with that. First off, we need an estimated duration, so we're just going to use the distance from the last waypoint to the current waypoint divided by maximum velocity. And we're going to check to see if we are currently on the ceiling and there is a random chance of the current path chance multiplied by 2. That means we are currently on the ceiling and we've decided that we would like to try and not be on the ceiling. So we're going to set last on ceiling to false. Now, what this means is that if our current path chance is 10%, then 20% of the time, if we're on the ceiling, we will try to come off of the ceiling. Now, this doesn't mean that we necessarily immediately come off the ceiling. It just means we have the chance of coming off the ceiling. Now, inside here, I am going to create a new if statement that just says if debug is active, let's build a debug line from the last waypoint to the current waypoint. And we're going to set its timer to 2 and its color to blue. And all this is going to mean is that if we are coming off the ceiling, let's go ahead and create a line that just marks us coming off the ceiling so we can use it as reference during debugging. And now we can go ahead and set our last waypoint to the current waypoint, as we've pretty much gotten everything we needed from the last waypoint. Now we're going to go ahead and create a new path waypoint here, and we're going to be using the pathWaypoint.new function, but we can't really create constructors in Godot scripts, so we're just going to have to assign all the variables right out the gate. So we create a new waypoint, then we set its waypoint normal to vector3.up, that's just the default, and its waypoint position to the current waypoint, as well as its waypoint not on floor to false, that means it is on the floor, and its estimated waypoint duration just to estimated duration. Now we can go ahead and say if we're not currently on the ceiling, we're going to check if a random f, which just means between 0 and 1, is less than the current path chance. This is why I said just because you set it to last on ceiling equals false does not mean it immediately jumps off the ceiling, because there is a random chance that it'll just decide to be on the ceiling anyways, and it'll go ahead and create a new up vector, which is used for the raycast to determine where on the ceiling we currently are pathing to. Now, for the current up vector, we're just going to use vector3.1 plus vector3.1 multiplied by randf range minus 0.5 multiplied by 2. All this is going to do is get a vector3 that's anywhere from -1 to +1 in any direction, plus vector3.1, which means that it'll always generally be above the current position. And we're going to use that as a normal for the raycast, and that'll just get a random direction somewhere up. Now, if that random value is not equal to true, which means we are not currently wanting to do this, we aren't currently wanting to be on the ceiling, then all we have to do is go ahead and add this to the current path and use the continue keyword, which is just going to go to the next for loop. So it'll just mean, no, I'm not on the ceiling and I don't want to be on the ceiling. I'm just going to add this waypoint as it currently stands with its waypoint position equal to the current baseline waypoint returned from the navigation system. And I'm just going to continue on to the next waypoint. Now, if we get past that, it does mean that we want to be on the ceiling. So in order to get that, we're going to go ahead and create a new raycast. And this is just going to be using the physics ray query parameters 3D.create function. We're going to be passing it in our waypoint as the the origin, and we're going to be passing it in our waypoint plus the current up vector multiplied by the up path check distance, which is just going to get us a position somewhere above the current waypoint in a random position. And we're going to use the world collision as the collision matrix and just use the space state.intersect ray with the query as the parameter, and that's going to return a result. Now in GDScript, all you have to do is say if result, then that means we have raycasted against something. We can go ahead and create a couple new variables here for the current distance, which is just the result.position's distance to the waypoint, and the current change delta, which is the absolute value of the current distance minus the initial wall roof distance divided by the initial wall roof distance. Now all this means is that that delta is going to be between 0 and 1 or greater than 1, and the higher the value, then that means that the more different from the baseline it is. So if our wall roof distance change allowance is 0.25, then that means that if this value is greater than 0.25, it means it is more than 25% different than the baseline, then we are too far separated and we need to go ahead and snap out of this. So if that is the case, we can go ahead and just set the last on ceiling equals to false, and that's all we have to do to make it no longer be on the ceiling, as we have already created a new waypoint up here to be used that is not on the ceiling. However, if that is not the case, then we do want to be on the ceiling and we have raycasted against the ceiling. First off, all we're going to do is if we're not currently on the ceiling, then we're going to go ahead and set our initial wall roof distance, as this is the first time we've raycasted against the ceiling, and we're going to set last on ceiling equal to true. Next up, we need to set up our new waypoint to actually be representative of the ceiling position. So we're going to set its waypoint position to the result.position and its waypoint normal to the result.normal. We're also going to set its waypoint not on floor boolean to equal to true. Either way, whatever the result of the raycast is, we go ahead and add it to our current path. And that's pretty much it for this for loop. Now we do need to do a couple other things before we can actually call this current path valid. And that's just going to be to check to see if the current path size is greater than 0. And if so, we're going to set the target position to the last waypoint position, so that way we know when we've reached the target position, and we can also use that in order to recreate the path. If in the future we get stuck, we can just call this function with the target path as the new target. And if it's not the case, we can go ahead and set the target position equal to the global position. And last but not least, for debugging sake, we're going to go ahead and create an if statement that says if debug active, then we go ahead and create a new variable, which is just going to be our global position, and we go ahead and iterate through all of the waypoints and create a line from the last waypoint to this waypoint with the color of just red and a duration of 5 seconds. Then we go ahead and set our last position to this position. That just means we iterate through all of the waypoints and create a line that is just the path that the AI is going to follow down. And that's pretty much it for the set target function. Now there's more functions that we need to go ahead and create. So first off, we're going to be creating the isTargetReach, and that's just going to return of type boolean. And all it's going to return is if the current path size equals to 0. So that just means we no longer have a path. That means our target is reached. We can also go ahead and create a couple functions for the normal. So we can get our current normal and our get ground normal. And our ground normal is just going to be the current ground normal, which is going to be generated using the grounding function. But then the current normal is going to be using the get next waypoint function. So let's go ahead and create that, as it doesn't currently exist. So first off, in the get next waypoint function, we're just going to check to see if the current path size is greater than 0. That means we do have a path. And our last retrieved path waypoint does not equal the first element in the current path. That means that we have changed the current path's first element, which means we have iterated through the waypoints. Then we need to go ahead and update the last retrieved waypoint. We're going to set the last retrieved waypoint path to the current path 0, and that's just going to be the first element in the current path. And we're going to set the waypoint failure timer equal to the estimated waypoint duration. Now, the reason why we go ahead and set this here is because we want to make sure that no matter what, we only call this waypoint failure timer update once, so that way we don't end up keep resetting it. I actually found that to be an issue in the earlier attempts of this. And we can go ahead and return the last retrieved waypoint path. Now, there is one other thing. If we haven't currently got a path, and our last retrieved waypoint path is equal to null, that means that this get next waypoint function has been called, but we've never actually been on a path, so we've never generated that first last retrieved path waypoint. Then we need to go ahead and create basically a stand-in. It's just going to be our global position with the vector3 normal of up and our waypoint not on floor equal to false. This way, no matter what, this function will return something, so that way we never get any null reference exceptions. Now, speaking of which, we do need a function to determine if we have reached the next waypoint path. So let's just create a new function called waypoint reached check. And this is not going to return anything. It's just going to be checking to see if we have reached the next waypoint. First off, we're just going to check to see if the current path size is greater than 0. If not, we're not going to do anything. And we're going to check a couple things. we're going to create a new delta, which is just going to be the difference between the current global position and the waypoint position of the first element in current path. And that's just going to be a vector pointed at the waypoint position from the global position. And we're going to create a new Boolean that says closer to next equals false and launch equals false. Both of these will make sense in a second. Then we're going to check to see if the current path size is greater than 1. This means there is more than one waypoint in the path. That means we aren't right at the end yet. We do have another path waypoint position to go to after this next one. We're going to set our two Booleans. Now our two Booleans are just kind of used to determine what functionality we need to actually use. So the closer to next just checks to see if the distance between our current waypoint position and our global position is greater than the next waypoint position and our global position. So if closer to next is true, that means we are closer to the next waypoint than we are to the current waypoint. The reason why I go ahead and check this is just in case we overshoot due to physics because of the way our AI works with physics. We want to go ahead and just set it to the next waypoint in line instead of trying to backtrack. Then we also have a Boolean to determine if we should launch. Now, if we should launch is determined based off of if our current path size is greater than 1 and our next waypoint does not equal the current waypoint's on floor value. So that means we're on the ceiling going to the floor in the next waypoint, or we're on the floor going to the ceiling in the next waypoint. Finally, we go ahead and check to see if our current delta's length is less than equal to stopping distance, or we are closer to the next value, then we need to go ahead and update our current path. So we'll just set the current path, remove at 0 function. That'll go ahead and remove the next waypoint. And if we do have a launch command, then we need to go ahead and set our launch attempt interval to the minimum launch delay, which will be subtracted in the physics process. And we go ahead and emit the signal for launch request. This should go ahead and launch us onto the ceiling. And if it fails, then the physics process will just go ahead and keep reattempting until it succeeds. Now, last but not least, we do need to go ahead and create the getGrounded function. Now, getGrounded is going to return a grounded state enum. And it's going to be a fairly complex function. Now, under normal circumstances, you just do a raycast downwards, but that's not really going to work out for us. First, we need to go ahead and do a sphere cast to see if we're near any walls whatsoever. So for that, we can go ahead and create a new physics shape query parameter 3D, and we can go ahead and create a new sphere shape to go inside of that. That's just going to be of type sphere shape 3D, and its radius is going to be the ground check distance. We can just go ahead and assign that to the sphere query.shape variable, and then we can also go ahead and assign our transform to the global transform, so that's just wherever the AI currently is, and our collision mask to the world collision. Next up, we can go ahead and get our space state, just like we did for the other function, and we can go ahead and assign our default current ground normal to vector3.up, just so that if anything doesn't collide with it, we go ahead and default to our ground normal being up. Then we go ahead and create our intersect shape function and return the result. Now, if we have a result, we're going to be returning a bit more of a complex function, but if we don't, we can go ahead and return grounded state.none. As we no longer are on the ground, we're not near anything using the sphere query, so we can go ahead and just default to none. Now, if we have got a result, then we go ahead and get our normal. This is going to be using the get current normal function. That'll be using the get next waypoint dot waypoint normal, which will just be whatever the normal should be. So if we're on the ground, that's just going to be up. But if we're currently crawling on a wall, then that should be some different angle pointed generally downwards. So if it is vector3.up, then we know we should be on the floor, so we're not going to worry about anything else. We're just going to return grounded state.floor. That way, if we happen to be on the wall slightly, but we are supposed to be on the floor, you should just go ahead and apply physics normally as if we're on the floor, and that should pull us right off the wall. Now, following that, we can go ahead and create a new raycast query, which we're just going to be using the physics ray query parameter 3d.create function, just like we did before. We're going to be passing it our global position, and then we're going to be passing it for the target position, a global position minus the current normal. So if we're on the wall, remember that is pointed down into the left or down to the right or what have you. By subtracting it, we're going to create a vector towards the wall from our current location, multiplied by the grounded check distance. And then we're just going to be using the world collision matrix as the collision matrix. And then we get the raycast result using the intersect ray function. Now, if that equals true, then that means that we are near the wall that we're supposed to be near. In which case, we're going to go ahead and set our current ground normal to the raycast result.normal. So that's whatever the wall nearest to us is. And we're going to be returning the grounded state.wall roof value for the grounded state enum. If that's not the case, then we're going to go ahead and return grounded state.floor. And that's pretty much it for the getGrounded function. Now, we do have one more function remaining, and that's going to be our physics process. Now, we have all of the helper functions, so we should be able to breeze right through the physics process pretty easy. First, we're going to check to see if our waypoint reached check, and then we're also going to be going ahead and getting our grounded state. We don't want to ever not get an updated grounded state, as this is used for other things other than just pathfinding. Next up, we're going to check to see if our target is reached. Then we need to set our desired velocity equal to vector3.0 and go ahead and return. However, if that's not the case, it means we do have another another waypoint to go to. So let's go ahead and get that. We'll use the get next waypoint function to create a new waypoint. And first off, we can go ahead and check to see if our current grounded state that we got up here equals grounded state.none. That means we're in the air. We need to go ahead and default our launch attempt interval to the minimum launch delay. This just means if you're in the air and you land, you don't immediately bounce back up. You give it a little bit of time for the AI to settle and reposition. However, if that's not the case and launch attempt interval is greater than 0, let's go ahead and subtract delta from it. Next up, we can go ahead and check to see if our current waypoint is not on the floor. So that means we are wanting to be on the ceiling. And our current grounded state equals the ceiling or wall. We can go ahead and set our gravity scale equal to 0. This means we are on the wall or ceiling that we want to be on. And we can go ahead and set our linear velocity minus equals the current ground normal multiplied by 0.5. All this does is add a tiny little bit of a nudge towards the wall constantly to kind of stick the AI to the wall or ceiling, and it's little enough that you can kind of just knock them off using physics, or they can knock themselves off pretty easily. Probably ought to set this as an actual parameter that you can modify in the inspector, but for the time being this works just fine. Now if this is not the case, that means we are not currently on the wall or the roof. We need to go ahead and try and get on the wall or roof because our waypoint is telling us that we need to be on the wall or roof. So we go ahead and check to see if our current grounded state equals floor and the launch attempt interval is less than equal to 0. That means we're on the floor and we've been there a little while. We can go ahead and set our launch attempt interval back to the minimum launch delay and go ahead and request another launch function. And regardless of the case, if we're on the floor or in the air, we need to go ahead and set the gravity scale to the internal gravity scale. That way we fall normal. And if our waypoint says that we're not supposed to be on a wall or ceiling anyways, we need to just go ahead and default our gravity scale to the internal gravity scale. Now besides that, we can go ahead and set our desired velocity equal to the current waypoint position minus the global position normalized multiplied by maximum velocity. This is almost identical to the way it was before. And last but not least, we can go ahead and check to see if we are debug active. Let's go ahead and build a line pointed towards our next waypoint position with the color of green. And this will just be helpful for debugging where the AI is trying to go. And that's pretty much it. Looks like this code is pretty good to go. Next week, we're going to be jumping back in with the AI controller in order to make them actually move along this code, as well as the limb controller to help with the launching and help with the foot positioning. But that's it for today. Thank you all for watching. As always, I know it's been a little bit of a longer video. I hope that this has been a little bit more digestible though. And we'll see you all back here next week for part 2 of this tutorial.